Hello student, the course of physics of linear and nonlinear optical waveguide. So, today we have lecture number 16 and we will going to study more about the material dispersion and related coefficients. So, today lecture 16. So, in the last class we defined the dispersion coefficient, we called it dm. By definition it is minus of lambda divided by c d2 n d lambda square, and if I want to find out the unit, it should be picosecond per kilometer nanometer, picosecond per kilometer nanometer, and we call this as dispersion coefficient. Well, apart from that, another useful coefficient is also used, especially in the pulse propagation problem in waveguides. So, another dispersion coefficient which we defined as beta 2. This is standard notation to define a dispersion coefficient beta 2, which is by definition d2k d omega square, and is called the groove velocity dispersion coefficient. Groove velocity dispersion coefficient. Now, one can realize this coefficient by expanding the propagation constant k as a Taylor series, which is a function of omega. So, if I expand around the wavelength around the frequency omega 0, this is the operating frequency. So, it should be this evaluated at omega equal to omega 0, and so on. This quantity is called the second order, because there are higher order also. Dispersion coefficient. This term, if we look carefully, it is 1 by Vg evaluated at omega equal to. So, at operating wavelength, what is the groove velocity can be defined by this term. Now, if I want to find out the value of beta 2, we can do that, because I know what is the expression of k, because k omega is omega divided by c n of omega. dk d omega I can calculate which we have already calculated. This is 1 by c n of omega plus omega dn d omega in terms of omega. In terms of lambda, it is 1 by c n minus lambda dn d lambda. In last class, we have already calculated that. Now, beta 2 is the second derivative of k with respect to omega, and if I do from this side, it should be 1 by c d of d lambda, because this is a function of lambda. So, eventually I want to derive this with respect to lambda. And using the chain rule, I should have d lambda d omega. Well, d lambda d omega and all these things is known. So, I will write here as 1 by c d n d lambda minus d n d lambda minus lambda d2n d lambda square, and this quantity also we know it is minus of lambda square divided by 2 pi c bracket close. Now, this quantity will going to cancel out. So, we have lambda divided by c multiplied by lambda square 2 pi c and d2n d lambda square. So, important thing is when you calculate the dn as a dispersion coefficient, we have an important term here, this one, which basically tells how the dispersion coefficient will going to change with respect to lambda, and d2n d lambda square is a factor that is sitting here. Also, in calculation of beta 2, I have a same factor sitting here. So, the calculation of d2n d lambda square is very important in calculating the dispersion values. So, this is essentially lambda cube divided by 2 pi of c square and then d2n d lambda square. This is my beta 2, another dispersion coefficient, and in units this is slightly different. This unit is picosecond square per kilometer. The unit become picosecond square per kilometer. So, for dm and beta m, both the cases the units are different, but both the things are measuring the property which is dispersion and very important property. So, once we know the derivative with respect to dn d lambda, one can find the value of beta 2, also the value of dm. So, there should be some kind of relationship, very easily one can find out the relationship between these two parameters, because in many cases it is required. So, the next thing is to the relationship between the two dispersion coefficient beta 2 and dm. M stands for the material dispersion. So, we already know what is dm. So, let me write it once again. Dm is equal to minus of lambda divided by c d2n d d lambda square, and beta 2 is lambda cube divided by 2 pi c d2n d lambda square. For this, the unit is picosecond per kilometer nanometer, and for this it is picosecond square per kilometer. Now, the relationship one can easily find. So, if I just make beta 2 divided by beta m, it should be lambda cube divided by 2 pi c, and then multiplied by this is 2 pi c square, by the way, because beta 2 is lambda cube divided by 2 pi c square. So, I miss a c square. So, it should be c square, and then dm is c divided by lambda. d2n d lambda square, d2n d lambda square, these two terms will going to cancel out. So, I have eventually 1 c square cancel out, 1 lambda, this cancel out. So, I have lambda square. Such eventually I have, so one negative sign is there, because so negative sign of lambda square divided by 2 pi and then c. So, my beta 2, if I calculate beta 2, I can convert this term to dm. If I calculate dm, I can convert the term to beta 2. So, this is basically the relationship between beta 2 and dm. So, if the value of dm is given, so you can calculate the value of beta 2 for a given lambda, and if the value of beta 2 is given, you can calculate the dm for a given lambda. Both the cases, they are measuring a quantity called the dispersion. Now, for normal dispersion, when the refractive index is increasing with respect to frequency, that we call the normal dispersion. So, for normal dispersion, we have beta 2 greater than 0, and for anomalous dispersion, this is another thing called anomalous dispersion. Beta 2 is less than 0. So, this is a very important concept, that for normal dispersion we have beta 2 greater than 0, and for anomalous dispersion we have beta 2 less than 0. Now, in different way one can understand the normal and anomalous dispersion. So, let me try it out. So, this is if the curve of dispersion, the refractive index as a function of lambda, and this curve is drawn in a normal dispersion regime. when the refractive index is changing with respect to lambda and decreasing. So, when the refractive index is decreasing with respect to lambda, then it is in normal dispersion, and when it is increasing with respect to lambda, then it is an anomalous dispersion. In frequency, if the refractive index is increasing with respect to, so if I draw this in a frequency domain, then normally what happened, the curve will be something like this. It will going to increase with respect to frequency, because with respect to lambda, if it is decreasing, it is increasing. So, both the cases, this figure is very much true for normal dispersion. So, this equation follows the Cauchy's relation. So, if I write the Cauchy's relation side by side, it should be, this equation is following this. So, it is very much in normal dispersion regime. This Cauchy's formula. Now, for normal dispersion, as I mentioned, we have dn d lambda is less than 0, and anomalous dispersion it is dn d lambda is greater than 0. So, the regime where dn d lambda is less than 0 is the normal dispersion regime, and in anomalous dispersion regime this is different. So, from this curve you can see that when the lambda is increasing, the n is decreasing. So, dn d lambda is essentially less than 0. So, we have a normal dispersion regime in whatever the curve is shown here. However, if I draw the full curve including the Selmayr relation, then it should be something like this. So, let me draw that. So, let me draw in a bigger. So, I have a wide range of lambda, and this is n lambda, and my dispersion, my refractive index curve is something like this. At some point here I have a discontinuity because this falls in near to the resonance frequency, and we know that at resonance frequency some sort of discontinuity one should expect. So, this is a region where we have an absorption band, and then there is a change of refractive index, and then suddenly again it falls like this, and we have again another resonance wavelength falling here somewhere, and in this region the refractive index is changing, and it is basically increasing with respect to lambda. That is why at this regime we will find the anomalous dispersion, and we have something like this and so on. So, here in this regime, if I look, dn d lambda is less than 0, because when the lambda is increasing, dn is increasing, dn is decreasing. So, this is called the normal dispersion regime. In this gap, we have d in d lambda greater than 0. So, this is anomalous dispersion regime. And these bands, by the way, these bands are absorption bands. So, these bands are absorption bands. Because if you launch a light at these frequencies or these wavelengths, what happened? There will be a resonance frequency. So, that means the molecule or these things will going to vibrate, and we should have an absorption in this region, and along this we have lambda. Well, this equation is valid here. N square is equal to 1 plus a lambda square divided by lambda square minus lambda 0 square. Lambda 0 here is a resonance wavelength. Now, what happened to the light wave when it is propagating in normal or anomalous dispersion regime, that we need to understand now. So, what happened is interesting. At normal dispersion, red light travel faster than the blue light. So, in normal dispersion, the red light is normally traveling in a faster with blue light, and we can see that with the expression of Vg. So, Vg is the group velocity, which is a function of lambda, and one can write as it is n minus lambda dn d lambda. This is the expression of that. Now, we also know the Cauchy's relation, and Cauchy's relation is valid for normal dispersion regime, as I mentioned. So, in function of lambda, the explicit form is something like this. Now, from here I can calculate dn d lambda, which is minus of 2b lambda cube, just a derivative of this expression. And Vg is now simply C divided by n, I write it as A plus B lambda square, and then minus of lambda, and then minus of 2b of lambda cube, which is essentially C divided by A plus this sign will be plus. So, it should be 3b divided by lambda square. So, that is the expression we have for Vg using the Cauchy's relation. Now, if I calculate for red, so Vg for red will be C divided by A plus 3b divided by lambda red square, and okay, maybe I can write this in a, so this lambda square, because since this is a red, so I can write it in this way. And Vg blue is C divided by A plus 3b divided by lambda square blue. If I try to calculate this term, 1 divided by Vg red minus 1 divided by Vg blue, then it should be A divided by C plus 3b, making the reciprocal, and then I just try to find out what is 1 by Vg minus 1 by Vg red and 1 by Vg blue. So, A divided by C, 3b divided by C into lambda red. So, I just put it as red. So, lambda square red minus A by C minus 3b divided by 3 lambda square blue. A by C will going to cancel out. So, eventually I have 3b. So, okay, these things will be C. I am making a mistake here. I write 3 here. So, it is C. C, I have the term 1 divided by lambda square red minus 1 divided by lambda square blue. That is all. Now, from this expression I can readily write that as lambda red, the wavelength of the red light, is greater than lambda blue. So, this quantity, from this quantity I can write 1 divided by Vg red minus 1 divided of Vg blue is simply less than 0, because if lambda is greater than this quantity, so this minus this should be less than 0, because this is this is lesser compared to this one. So, 1 by Vg of red should be less than of 1 by Vg of blue, and from that we can conclude that Vg of red should be greater than Vg of blue. So, this is essentially the thing we try to find out using the concept of dispersion, how the red light is propagating in normal dispersion regime, how the red light is propagating as a first red compared to the blue light, that we try to prove, and this is basically a proof of that using the basic Cauchy's relationship of refractive index as a function of lambda. So, with this note I would like to conclude here. So, in the next class we try to understand that how the pulse will going to broaden in a more rigorous way. So, with this note let me conclude. Thank you for your attention.